Hello, Doctor. Good afternoon. Are you hear me? Dr. Liang?
Hi, Dr. Liang. Could you hear me? Hello. Hello, everyone. This is for the section of functional composite materials. Dr. Liang, could you hear me? Hello, I guess the internet of Dr. Liang is not very good. The first speaker is from ACE Engineering College. The talk is Studies on Synthesis and Characterization of Nanofilms of Polymer Blends of Polymers and Acetate. Is the first speaker here? Is the first speaker here? I think the first speaker is not here. And I also don't have the video from the first speaker. Maybe we can wait until 3:30 for the second talk.
That's it. Eh? Now you can talk.
Hi, hello. Can you hear me now?
Yes, we can hear you.
Oh, yeah. Sorry about the technical issue.
Yeah, the first speaker is not here, and we also don't have the video from him. So
Yeah.
I think we can just wait until the second talk, which is at 3:30 p.m.
Okay, yes. The second speaker just typed a chat saying he's going to play the pre-recorded presentation. So for his own computer. Okay.
Yeah, from himself, I believe.
Yeah, actually, the reason I run into this kind of technical issue because I'm trying to play those from my computer, but I got the audio quality is quite bad. So I don't know how do you get a good quality, audio quality when playing the videos?
I'm not sure either. Sometimes it happens with how you set the display.
I see.
Yeah, the ratio of the display. But never mind. I have the videos, and I can help with them. Yeah.
Thank you.
No problem.
Hi, everyone. So I think it's time we get started. Hi, is the second speaker here? Yes. So yeah, I guess we can let the second speaker take hands now. Okay. Yeah, you can get started anytime you want.
I don't think we can hear you.
I cannot hear you. Can you turn off the volume? Yeah, we cannot hear you clearly. The volume is too low.
Okay.
Oh yeah, cool. It's much better now.
I think the sound of your video is not displaying properly. But if you want to talk by yourself, it should be okay.
No, the volume is still very low. We cannot hear you.
Well, I'm sorry, I'm having technical problems. Maybe you can play the pre-recorded presentation from your computer, and then it will fix the sound problem, because I cannot do anything.
I don't think I have the video. It's not uploaded in the Dropbox, so I don't have the video.
It is uploaded. I have uploaded it.
You just did?
No, I uploaded it after the rehearsal on the 10th of August.
I don't think so.
Yeah, I didn't have one either. So we didn't have the video somehow. Let me double check. Right now.
There is a host for this meeting room. I think he also couldn't find your video in the Dropbox.
No, we couldn't find your video.
Yeah. It's
okay,
not
because in this case, I just have much less time since I started. So obviously I can present now, but the problem is I just consumed a couple of minutes of my time.
Just go ahead. Go ahead with your presentation. It's fine. Just go ahead.
Well, but you can hear my own commentary superimposed on me talking, which will make things even fuzzier, because I will be talking over my pre-recorded voice, which I cannot get rid of because it's a part of the presentation. Unless you can hear what I'm saying and the commentary is much less pronounced and you can ignore it. Otherwise, it's going to be a cacophony of sounds with me talking over my own pre-recorded voice. That's the problem.
Do you have a PowerPoint slides?
You can hear what the problem is. I'm talking over on my own voice, which is pre-recorded. So I'm, it's very disturbing because my presentation already contains the audio commentary.
Oh, I see.
And I cannot easily produce another one just in this very moment without the audio commentary, because I was prepared to talk like this, just to play it, assuming that the sound quality will be enough at your side.
Yeah, let's just go ahead with the option you prefer.
Well, maybe I can try to present it like this, from this view, and just this will cause the sound not to be broadcast. All right, so in the remaining time, I will have to improvise, I'm sorry. So what I wanted to talk to you about...
Sorry, not to interrupt. You haven't started to share the screen.
I'm sorry, I am sharing the screen. That's the problem. I am sharing the screen.
We're just seeing a blank screen.
What about now?
Yes.
All right. So in the 4 remaining minutes, I would like to talk to you about proton conducting mechanism in BZ-COI72 perovskite oxide proton conductor. The aim of this study was to actually answer 3 main questions. What is the exact number density of protons, which is actually very difficult to elucidate using other techniques than neutron Compton scattering? What is the mechanism of proton conduction? Because it is believed to be a Grotthuss mechanism, a combination of rotational diffusion of protonic defect and transfer of the proton from oxygen to the nearest neighbor. It is known from spectroscopy that hydrogen bond is formed, but we don't know whether the mechanism of proton transfer is a classical one, a hopping, or is it a quantum one, whereby you have a coherent superposition of the proton wave function and then basically a proton tunneling mechanism. And what is the nature of local binding potentials of metals present in this perovskite oxide system, which are barium, zirconium, cerium, yttrium, and how tightly bound is oxygen? All those questions can be answered using neutron Compton scattering. So the plan of this work was to first elucidate the structure using neutron diffraction on the very same spectrometer that records Compton scattering concurrently with Compton scattering, use the structure for ab initio prediction and validate ab initio predictions against neutron Compton results and answer hopefully all those questions. So the question about the structure has been addressed by analyzing the neutron diffraction, and it has been confirmed that there is a phase transition as reported in the literature at 85 Kelvin from orthorhombic to rhombohedral structure. Partial occupancies of metals in this framework have been also confirmed. And the problem with hydrogen was that even using neutron diffraction, hydrogen positions were not very well characterized. So it has to be assumed in further studies that we take the structure solved and we don't place partial coordinates of hydrogen. We just use the structure without hydrogen, accounting for hydrogen indirectly by lattice distortions in the modeling, and try to come up with the predictions for the vibrational density of states, partial vibrational densities of states of zirconium, cerium, yttrium, oxygen, and barium in this material. And what we are interested in are the centers of gravity of those, because they are proportional to nuclear kinetic energies that can be directly measured by time of flight neutron Compton scattering and compared with the experimental results. When we do it, we can plot the width of momentum distribution, which is a square root of kinetic energies as a function of temperature, and then compare it with lattice dynamics prediction. And we know from the theory that whenever we see a result from experiment which is actually showing overbinding, so higher width of momentum distribution compared to lattice dynamics prediction. We have quartic time anharmonicity. Whenever you see something which is softening of the mode, so smaller kinetic energy, we have cubic type of anharmonicity. So we can characterize the anharmonicities of all those local binding potentials of all metals and oxygen present in the perovskite oxide lattice by using Compton scattering. We can also measure the proton momentum distribution function, which is a square of its wave function. And it is Gaussian, which means that the mechanism of proton conduction is classical. So we have classical hopping instead of coherent tunneling across the hydrogen bond. Moreover, we can plot the stoichiometry, the number of hydrogen atoms per formula unit as a function of temperature, and it is constant, 0.2 protons per formula unit, which is commensurate with the total vacancy concentration as predicted by literature. And also by measuring the width of proton momentum distribution as a function of temperature, we can see that across the phase transition, it is actually protons become more localized in space and delocalized in momentum, and above 200 protons become delocalized, creating quite a fertile ground for the onset of proton conduction at higher temperatures. So I would like to acknowledge my collaborators, Angela Krut and Jan Wallis from Leibniz Institute of Plasma Science, who prepared the sample and characterized it prior to neutron experiments, and my fellow instrument scientists from Rutherford, Appleton, Ivan da Silva, for conducting the structural elucidation from high resolution neutron diffraction data collected on my instrument. Thank you very much for your
interruption. Yeah, sorry about technical issues. So can the third speaker, I just want to save time. Can the third speaker start to share the screen? Nivenio Papasmil from USA. The third speaker. Is the third speaker Nivenio Papasmil here? From LAAS. Is the third speaker here? I guess we will have to play the pre-recorded video. Qi?
Yeah, I am going to.
Hello, I introduce you today in composite micro-nano heterostructures for nuclear power applications, a novel domain that was developed in the last 40 years. I'm Liviu Popa-Semil, scientist in nuclear engineering and physics, specialized in nuclear application, nuclear materials, directed energy, pulse power, analysis, energy-related devices, and so on. Between 1981 to 2000, I worked as senior scientist, project manager for Romania Institute for Physics and Nuclear Engineering in Bucharest, then for Los Alamos National Laboratory, and since 2006, I'm the president of LLVM LLC, a private company involved in nano engineering and terahertz applications. Since 2010, I became the executive director of LAAS, a non-for-profit organization involved in betterment of the society, stimulating inventions and business. The actual nuclear power trend is clear for many, and they already starting talking about a renaissance of nuclear energy, but most of them avoid to admit that without solving the big problems it has today, there will be no tomorrow. We have the cost of the energy higher, and nuclear is among the most expensive power supplies. Then is the controllability. Nuclear power is a based load energy as coal, and it's difficult to follow the curve of demand using the nuclear power. The actual technology presents a lot of inert accidents, and this is a diagram of the accidents as a function of inert level. And the new technology have to have a much lower accident rate. The actual technology has also a high problem related to waste deposition, and we are looking forward to reducing the lifetime of the waste fuel inside the deposit. And here is the main process. Here is how the fission takes place, when it mentions that inside the nucleus it's a soup of quarks, it's not a bunch of separate balls as protons and neutrons. The fission product is stopping in the lattice and is starting to produce defects and recoils and substitution atom impurities, and we need to deal with all of it. Here is a table of elements, and you will have the number of neutrons, and you'll have the number of protons on the scale, and these are the radioisotopes. Here is how the fission products are landing into unstable areas like this one and this one of lower mass, and by decay reactions are navigating toward the stability island, the black dots in the map. After a while, by integration of the mass, you will see the fission product distribution for various type of material, fissile material as plutonium, uranium, uranium-233, and various neutrons energies. Here, an important part is what are the problems in the actual nuclear reactors. The fuel is cracking. The fission products are accumulating, making the fuel brittle, and they are chemically react with the fuel. Also, the temperature distribution inside the fuel pellet makes it prone to cracking because of high expansion in the core, and ceramic is not so resilient. Also, as the materials have different conductivity, and this is a complex structure of events that can happen in the actual nuclear fuel, limiting the This is the simple product. It's called Gerlig Mesh, and it's a spherical structure of plutonium carbide to uranium dioxide coated with titanium tungsten carbide or other inert material to chemical process. Just makes the fission product exhibit the Bragg peak outside into a liquid metal and have a microflow associated. A nanoflow is used to deal with the transmutation products that have smaller ranges, and these are nanomaterial, nanobeads, that use also advanced nanocluster properties to eject the new products out and being washed by a fluid outside. This is how a nanobead structure looks like, and here are some patterns. Here is a pebble bed reactor-like fuel, but it's a micro level, few microns coated in graphite, but has issues about heating, and here is how it looks like. But this is a dispersion theory, appeared in 1950s, and they observed that the smaller the fuel is done, the better it is for fission product damage. And here is what we are aiming with a new product. This is the operation temperature for the pellets, and this is the burn-up factor. And we need to move the curve of failures from this point to this line that allow higher burn-up and higher temperature. And there is a large variety of material you can use for drain fluid, for cladding, for coolant to make a pellet again. From thermal conductivity, when mixing a ceramic like uranium dioxide, urania, with a liquid bismuth eutectic fuel or liquid sodium, you have various operation temperatures, but the thermal conductivity is moving into the middle part and you have better conductivity. This is how a fluidic channel look like, and these are the Bragg peak from the fission products taking place in the liquid, because in liquid is not. There is also advantages of using simple separation and recladding by thermal processing and distillation, and you separate the fission products in gas, liquids, precipitate, and simply you reclad and reprocess the nuclear polymers. This is how a pellet looks like, containing bigger particles and the borders and smaller particles into the center, allowing the fluid to flow continuously. Here is the experimental reactor, a VVRS, 4 megawatt research reactor with 10 to 13 neutron per square centimeter second as a neutron flux, and use a vertical irradiation channel to introduce the experimental samples for this nano product. And this is the advantage. In actual technology, we deal with this fission product amount in the fuel, but in the liquid, we have much less because not all of them are collected. And also, we have a high concentration of transmutation products. A complex structure uses the micro heterostructure to deal with the fission products, and inside it's embedded nanocluster structure to deal with the transmutation product with the flow circuits. But this is very complex to build, as is shown in the figure. Here is how it looks like, the microflows that can be used inside the closed pellet, a sealed one, or you may use an open circuit where you have a heat exchanger and separation, and you separate into beta decay and take the fission product out immediately, not leaving them to absorb one more neutrons. Here is the safety that is improved because having fission products out at a sudden stop of the reactor, you don't have to deal with this curve of remnant energy that in 1 second you have about 7% of operation power in a heat you need to remove, and only in about 10 days to go down. The economics is complex because at the first sight Gerlig Mesh fuel is more expensive, but when you take in account all the processes involved, you end up with a cheaper to use fuel, and the global cost is reduced by a factor of 8 to 10 of resisting to burnup. The fuel cycle, the nuclear fuel cycle, is a very complex one, but the new materials may interfere with the enrichment, reducing the need of enrichment and allowing the fuel reprocessing, and the breed and burn technology with simple fuel recladding in the place of burnup, not needing too much storage deposition. As you know, material is very important, and from the past, Damascus sort were not possible without Damascus steel and all the technology related. Now, as Albert Einstein and Niels Bohr once talked.
Yes, so I guess it's time to move to our speaker number 4, and Ajit Maycap. Is Ajit Maycap here? From National Institute of Technology, from India. Is the speaker number 4 here? Yeah, I don't think so. I guess we need to play the video.
Good morning, everybody. I am Ajit Kumar Maycap of National Institute of Technology, Durgapur, India. Convey my sincere thanks to organizer for selecting our above paper for oral presentation in the conference. Outline of the talk is as below. Materials with enhanced dielectric properties are in constant demand for energy storage device material. Inorganic ceramic materials show high dielectric constant, but inherent brittleness and bulky properties limit their application in soft flexible devices. The aim of this work is to design a flexible polymer CNT composite materials with enhanced dielectric constant with low dielectric loss. Properties of carbon nanotube are well known to all. They possess good thermal conductivity, mechanical and electrical properties which are valuable for different fields of material science and technology. Among the polymer, PVDF is most widely used due to easy processability, easy film forming properties, good dielectric strength. The structure of different phases like alpha, beta, and gamma of PVDF are shown here. The samples are prepared by simple solution casting route, which is described in the figure. The prepared samples are characterized as S0, S1, S2, S3, and S4. The film of thickness 0.106 millimeter and area 9 into 12 millimeter square has been prepared. Silver paste contact was applied to the opposite faces of the sample for electrical measurement. The experimental setup for the dielectric measurement for temperature range 300 to 423 K are described in the figure. Morphology of the films are described here. The sponge-like structure has been observed for pure PVDF, whereas due to addition of MWCNT, sponge-like structure almost disappear. AFM analysis clearly demonstrates the dispersion of MWCNT into the polymer matrix. The analysis of the HPIR peak suggests the existence of the alpha, beta, and gamma phases of the film. The beta phases of the PVDF with high intensity in the S2 sample reflects the presence of the high order beta phase contribution in the PVDF WCNT-CWH system. The Raman spectroscopy has been studied for further clarification regarding the presence of different phases of PVDF and the effect of the functional group on the matrix pillar interface interaction. The alpha, beta, and gamma phase of PVDF are shifted to higher frequency due to strong interaction between CWH group and CF2. The intensity ratio I alpha by I beta and I gamma by I beta reduces from 0.37 to 0.19 and 1.25 to 0.81, indicates the addition of the functionalized MWCNT allows arranging polar beta phase compared to the non-functionalized MWCNT. The XRD analysis suggests that the degrees of crystallinity reduces for functionalized MWCNT PVDF than pure MWCNT PVDF, because for functionalized MWCNT, due to presence of functional group on the surface, TTTT conformation of PVDF cannot able to well match with the zigzag carbon atom, so degrees of crystallinity decreases. The frequency variation of AC conductivity with temperature has been shown here. The frequency exponent case can be calculated from the slope of at the straight line part of the curve. The frequency exponent for S1 sample is purely temperature independent and follow the quantum mechanical tunneling model, whereas for S2 sample it decreases which follow the correlated barrier hopping model. The conductivity value enhances with an increase in temperature, probably due to the enhancement of free charge contribution to the composite system. The dielectric constant significantly enhances for functionalized MWCNT PVDF film over pure MWCNT PVDF film. However, the dielectric loss is significantly lower in functionalized MWCNT PVDF film compared to pure MWCNT PVDF film. The Bordet plot of the impedance spectroscopy at different temperatures of S1 and S2 sample has been shown here. A prominent relaxation peak has been observed which shift to the higher frequency side with an increase in temperature, and this reflects the relaxation time loss with an increase in temperature. The frequency variation of electric modulus has been discussed here. The value of parameters C and D in the equation indicate the deviation from Debye model at low and high frequency region. The analysis of the data suggests that the deviation from the Debye model is less for S2 sample compared to the S1 sample. The normalized electric modulus for S1 and S2 sample are demonstrated here. The normalized curve for S1 sample do not match on the single master curve, although for S2 sample overlap on a single curve. So for S1, the dynamical properties change with temperature, whereas for S2 sample, it is temperature independent. The resistance voltage plot engraves the formation of the hysteresis loop of the nanocomposite film and indicate the memory storage performance of the film. The low value of the skin depth and high dielectric constant of the film makes it a promising candidate for designing flexible and cost-effective electronic devices. A clear electric hysteresis in current voltage behavior has been observed for all samples except S1 and S4. Initially, increasing voltage from 0 to 50 volt current value is high, so a high conducting state have been observed. In this state, a local conducting path of low resistivity may be generated. Now, for decreasing voltage from 50 to 0, current suddenly drop and does not follow the same path. At this time, some dipoles are trying to back in its initial state, then free charge carriers are maybe trapped inside the drain and drain boundary, which decrease the value of the current. Static and dynamic conductivity of the different samples are plotted here. It is observed that for S1 and S2 sample, both the conductivity value is high and it does not change with temperature, whereas other samples, it shows the temperature variation. So by changing the functionalized group of MWCNT, we find different conducting behavior of the functionalized MWCNT PVDF film. The variation of polarization with electric field has been shown for different samples at different hysteresis period. We observe periodic electric hysteresis loop for S0, S2, and S3 except S1 and S4. The increment of remnant polarization with hysteresis period for S0, S2, and S3 has been observed. This is because with increasing time, more dipoles are able to orient in the applied field direction. The enhanced energy storage capacity has been observed in functionalized MWCNT PVDF composite film, which can be used for development of flexible energy storage devices. In conclusion, FTIR and Raman studies suggest the formation of polar beta phase of PVDF in the composite. Enhanced dielectric property have been observed with ferroelectric hysteresis loop. The energy density of the film is very high, so it can be used as energy storage materials. The references are given here. Acknowledgements. Thank you.
Okay, so our next speaker is from Valentin Mangrev from University of Chemistry and Technology, Prague. So is the speaker here? Is the speaker published from Prague here? No, I don't think so. Chi, can you play the video?
Sorry, I don't have the video from this speaker. You can just wait to the next talk.
Sorry, what do you mean? Can you repeat?
Oh, I don't have the video from the speaker.
Oh, you do not? Okay, so, but the speaker is not here. Okay, so I guess I wonder we should have, let the second speaker talk again. Do you think that's a good idea? Well, yeah, I guess we can just take a short break and wait until 4:10 p.m. So to start the next talk.
Okay. Yeah. Thank you.
So, by the way, is it just me or the video quality is a bit, the resolution is a bit low?
I'm not sure. It's displaying like properly on my screen. So
Yeah.
I don't know how other people look at it.
Can anyone else confirm? So is the video quality, the picture resolution is good or bad? So it's just me. Well, okay, that's fine. If it's just me, that's totally fine. Okay, yeah, thank you.
Yeah, the audio quality was not that great. Yeah.
the audio quality is good. The audio quality is good. The video quality, the picture, the resolution of the PowerPoint slides is a bit low. But if that's just because I have a bad connection, that's fine. So as long as other participants, audience can see the video clearly, that's totally good. Is the next speaker Tanushree Chowdhury here? Sorry if I butcher your name. Is the next speaker Tanushree Chowdhury and from India here? I saw your name in the participant list.
Please unmute me.
Yeah, I think you're unmuted now.
Okay, thank you. Yeah, thank you.
So I saw your video. Your video has like a 15 minutes long.
Yeah, I sent the video, but I again confirmed that I would be presenting online.
Oh, okay, in 10 minutes. Okay, yeah, because yeah, that would be much better. Okay.
Yeah.
So, okay, let's wait for 1 minute so I will let you get started.
Okay. Shall I proceed with the presentation?
At least you can start share your screen.
Yeah,
Share your
sure.
screen so we can test if everything is all right.
Yeah. Is it visible?
Okay. Yes, we are seeing the screen.
Is it there?
Yes. Yes.
Okay. Shall I
Just wait for 1 minute. Just wait for 1 minute. Okay, I think you can get started.
Okay, I'm starting then. Okay. So I am Tanushree Chaudhary. I am presently working as an assistant professor in chemistry division from VIT Chennai. And today the title of the talk is Synthesis and Characterization of Titania Pellet Clay Membranes for Methylene Blue Degradation in Textile Wastewater. Now, as we see, what is wastewater? Wastewater encompasses a wide range of potential contaminants such as methyl orange and methylene blue dye. And these dyes are in very low concentration according to Environmental Protection Act. These dyes are in low concentration in the wastewater, and therefore their removal is a challenge. So titania has been used as a widespread photocatalyst for treating such contaminants. But the main problem with titania is about a small surface area, and also its low absorption ability. So therefore, the need of the hour is to develop a composite membrane, that is a composite material, which can serve as the multifunction of separation and photocatalysis, and which can provide a novel solution to that is a novel process, a novel and sustainable process of wastewater treatment. So we have used, that is the clay, which is this typical structure of Montmorillonite clay. This is a 2:1 structure. So this has, if you can see that this has the ability, that is has a very important property of cation exchange capacity. And because of that, polyhydroxy metal cations, they can be easily exchanged with the aluminium or magnesium ions in the interlamellar space of the clay. And and upon calcination, they can give rigid oxide pillars, and these pillar clays, they provide very attractive materials for that is for serving as membrane material, because the pore size can be controlled by just by just controlling or modulating the different parameters during the pillaring process. Now we have used that is ceramic membranes. We all know that ceramic membranes have an edge over the polymeric membrane because of its that is various properties such as mechanical stability, chemical stability, and thermal stability. So we have used the ceramic membranes with an asymmetric configuration, that is of a base support material made up of clay and with inner and a top layer of titania, which can provide a low cutoff value and high fluxes. And of course, natural clay is chosen as a support material because it can provide, that is, it has a host of properties. That is, it is easily available at low cost. It has excellent mechanical and thermal resistance. It has a large specific surface area, very high cation exchange capacity, and extremely good binding capacity as exhibited by its structure. But why did we choose the titania pillared clay membranes for our topic? Because titania pillared clay membranes, so first of all, the selectivity of the membrane depends upon the top layer or the active layer on the membrane support. And this is made up of titania. So titania offers a host of properties. So as we can see over here, a lot of important properties are mentioned, but I would like to concentrate on two important things: that it has extreme photoamphoteric character. And because of that amphoteric character, it exhibits unique surface charge characteristics at different pH values. And also it has extreme photostability, and that is why it provides an integration between the membrane and catalysis for separation process. And also that this possibility of using this titania pillared clay material as membrane has not been explored till date. The methodology that we have adopted is the simple sol gel process in the laboratory. We have used titanium 4 isopropoxide as the starting precursor, have added water and isopropanol to it, which underwent hydrolysis, acid hydrolysis at 2 different pH, that is pH 2 and pH 3.5. We have chosen 2 different pH to ascertain the structure of the membrane material. That is why we have chosen 2 different pH. So that underwent acid hydrolysis and condensation to give the titania sol. With the titania sol, we have made the supported membrane material and the unsupported membrane material. The supported membrane material was made by dipping in the that is the membrane, that is the flat disc support into the titania sol, and then it is sintered at various temperatures, dried and sintered at various temperatures from 300 to 600 degrees centigrade. Whereas the unsupported membrane material is made by draining of the excess sol from the support, that is from the support material, and then that was dried and sintered at various temperature from 300 to 600 degrees centigrade, and that provided the basis for the characterization purposes. So this is the entire synthesis procedure that has been shown as a flow chart. So we can see that is the flat Dutch support. Then over there is the interlayer of titania and binary interlayers of titania and clay. Two different pH values were chosen, pH 2 and pH 3.5, which gave the titania pillared clay membranes that was formed by dip coating. That was used for membrane rejection test. These are the nomenclature of the different membranes that were prepared. We prepared around 24 membranes out of this, out of which 12 membranes were supported membrane and 12 were unsupported membranes. The characterization part includes, as we can see, that is in the figure 1 and 2, that is FTIR spectra at two different pH values, that is pH 2 and pH 3.5. We can see very clearly that the silicon oxygen silicon stretch peak at that is 1049.31 per centimeter has been completely lost, which indicates that the intercalation of titanium 4 ions, metal ions, into the that is the interlamellar space of the clay has been made possible. In the XRD figure of figure 3 and 4, we have seen that as we can see over here, that is XRD diffractograms that were taken at two different pH values, pH 2 and 3.5. We can see that there is a presence of anatase peak. So this anatase peak is prominent at all temperatures. From 300, we have sintered the membrane materials at different temperature, from 300, 500, and 600 degrees centigrade. And it has been seen that is this peak, that is anatase peak, is very prominent at all temperatures. And anatase has extreme that is photocatalytic activity. Then figure 5 and 6 represents the determination of surface charge by that is zeta potential measure experiment. So as we can see over here in the figure 6, the zeta potential measurement, that is it's less than minus 25 millivolt. So it denotes the extreme photostability. It denotes extreme stability of titania in aqueous solution, and also it suggests that at pH 3.5 the titania is stable. The dispersion of titania is stable. In figure 7 and 8, it reflects the pore size distribution at pH 2 and pH 3.5. We can see that pH 8 and pH 3, they represent the titania and the titania clay composite membranes at that is 300 degrees and which is sintered at 300 degrees centigrade, and at pH 3.5, it is showing a very narrow that is pore size diameter, and as compared to the other materials. So we can say that is at pH 3.5, not only it is stable, the titania composite membrane, not only it is stable, but it also when it is sintered at 300 degrees centigrade, it is giving a very narrow pore size diameter, which can give a very high cutoff value and also high flux. Now, this is the membrane materials that the SEM, that is a scanning electron micrograph of different membrane materials were taken, which were sintered at 300 to 500 and 600 degrees centigrade from clockwise direction. As we can see, that is the prominence of anatase peak in all the anatase phase is prominent in all the that is at all temperatures. We did the membrane rejection test with methylene blue dye. So as we can see over here, that is in the membrane rejection test, that is most of the membranes they are giving, that is around 100% rejection, that is at 300, 500, and 600 degrees centigrade. And this is because of the presence of the anatase phase, which has degraded the MB dye. So in a conclusion, I would like to summarize as we have seen, that is now the pH is one of the most important parameters that is expected to affect the effective rejection of organic compounds. The surface charge of the material is very important. It depends on the pH of the feed solution, and is a very important parameter for realizing the efficiency of the membrane separation process. Anatase is the most prominent phase that is formed, and it has the best photocatalytic activity, and that is why it is at effects in 100% degradation of the MB dye. So thus, by controlling the surface charge, it can lead to selective removal of pollutants. And also titanium pillared clay membrane material, which has been synthesized at pH 3.5 and sintered at 300 degrees centigrade, shows the best results and can be used as a low-cost membrane material for further applications if we compare it with the values of alumina membrane. I would like to acknowledge this work as a part of the Water Initiative project, which has been funded by the Department of Science and Technology, Government of India. And thank you all for that's giving me an opportunity to present my work at this prestigious platform. Thank you.
Well, thank you very much. So do we have any, we can take one short, quick question.
Yeah, I resume. I think, yeah, I'm working as an assistant professor in that is in VIT, that is in chemistry division, and my work includes that is characterization and synthesis of polymer clay nanocomposites. I work on membrane. At present, I'm working on membrane separation processes, and I've also worked on developing of clay catalysts for industrial applications.
Okay, cool. Thank you. So I guess we need to move to the next speaker now. So thank you very much.
Thank you.
The next speaker is Bansi Kao from Switzerland. Is the speaker here? Bansi Kao from Switzerland. I don't think so. I don't see him from the participant list. Can you play his video?
Sure, I will.
His video has only 3 long, and
yeah, it does 3. Yeah.
I don't know how it can work. It doesn't have audio, right?
It looks like it doesn't have audio.
It doesn't, yeah. So it's not just me, it doesn't, and it's only about 3 minutes long. So, well, I guess we just let it play for 3 minutes.
Mm-hmm.
That's it. Okay, I guess we can take a short break. So since this speaker only has about 3 minutes to talk, So, and let's take a short break, and we convene around 4:28, 4:20, maybe 4:28. Is the next speaker Matthew Bauchi from UCLA here? So, well, I guess he's local, right? So I hope he's here since he's local.
And I don't have the video from this.
Yeah, I know you don't have his video, but
Mm-hmm.
he's local, so he should be here. But I don't see his name from the participant list, which is not good. Yeah, I guess let's wait for a few minutes.
Sure.
Is the next speaker Matthew Bauchi here from UCLA? speaker from UCLA, Matthew Bauch here? One more time, is speaker Matthew Bauch from UCLA here? No, I don't think so. Well, I guess we're gonna have a longer break now until let's reconvene around 4:38 p.m. So another 8 minutes break. Hello again, everyone. So let's back to our session. And our next speaker is Alexandra Ivanova from Spain. So is the speaker here? Speaker Alexandra Ivanova from Spain. Are you here? I guess not. Hi, Chi, can you play the video?
Yeah, sure.
Hello to everybody. I'm so pleased for the opportunity to present one of our works. First of all, I will start with a constantly growing problem, antibacterial resistance. The discovery of antibiotics was a revolution for treatment of infectious disease. However, the bacteria had programmed to survive. Many bacterial species became resistant, some of them multi-resistant. The problem with the antibacterial resistance is that many treatable bacterial infections became incurable. Bacteria can neutralize antibiotics by different mechanisms, such as antibiotic degrading enzymes and antibiotic altering enzymes. Often the bacteria live in biofilm structures composed of cells and extracellular polymeric matrix, which limits the antibiotic penetration, making the CCL cells up to 1,000 times more resistant than the planktonic cells. The biofilms can grow on living and non-living surfaces, causing difficult to treat infections. Here is some warning statistical data. 1 in 10 patients in hospitals is infected. 80% of all infections is due to the formation of biofilms on medical devices. 25,000 people die every year from drug-resistant infections. The multi-drug-resistant bacteria cause huge financial loss. So herein we have developed smart drug delivery nanosystems. Emery is loaded into borosilicate nanoparticles frameworks, and elastin is used as a stimuli responsive gatekeeper upon the elastase production by Pseudomonas aeruginosa. Alginate lyase breaks down the biofilm matrix and allows the nanoparticles penetration into the biofilm structures, enabling the drug release and eliminate the pathogen. So this drug delivery nanosystem inhibits the biofilm establishment and eradicates the drug resistance biofilms without inducing toxicity and selective pressure for resistance development. The advantages are lower dosage of the active agent, enzyme responsive delivery of the active agent, and lower risk of resistance development. So, as we say, the borosilicate nanoparticles were loaded with imipamine and subsequently coated with elastin, polyethylenimine, and alginate lyase in a layer-by-layer strategy. The encapsulation efficiency was determined with 28%, and the drug concentration was 140 micrograms per milliliter. The variation of the potential volumes confirm the successful layers deposition. The TM images indicated spherical shapes of the nanoparticles with mean size of 250 nanometers. So the ability of the developed nanoparticles to inhibit the biofilm colonization and biofilm formation was evaluated using 2 assays. Crystal violet assay was used to quantify the total biofilm mass. The drug-loaded nanoparticles demonstrated strong anti-biofilm activity due to the bactericidal activity of antibiotics and its boost release. Good biofilm inhibition properties showed the drug-loaded nanoparticles loaded with antibiotic and coated with elastin. The layer-by-layer nanoparticles with upper layer of polyethylenimine didn't inhibit the biofilm formation. The best biofilm inhibition activity was observed when alginate lyase was decorated on the layer-by-layer mesoborosilicate nanoparticle surface. The enzyme broke down the alginate and impeded the bacterial attachment and the biofilm formation. Meanwhile, the imipamine eliminates the bacteria. To highlight the importance of the enzyme, we used non-active protein as a control. No biofilm inhibition properties was observed. So the cell viability within the biofilm structures was studied using live dead kit assay, as we can see on the microscopic image. And the bacteria form well-established biofilm. The drug-coated mesoporous silica nanoparticles showed bacterial killing properties. No bacterial inhibition activity was observed in the other controls. The antibiotic solution in the layer-by-layer mesoporous silica nanoparticles with alginate layers as upper layer impeded the biofilm formation. So it was important to evaluate the ability of the nanoparticles to eradicate already established biofilms. High concentration of the drug-coated mesoporous silica nanoparticles would need to eliminate the drug-resistant biofilms due to the booster release of the antibiotics from the nanoparticles. However, only the layer-by-layer mesoporous silica nanoparticles with upper layer of alginate layers demonstrated 80% reduction of the biofilm mass at very low concentration of the active agents. Similar results we can see from the live dead kit assay. We saw that established biofilm was resistant to the antibiotic biofilm solution. Only the layer-by-layer mesoporous silica nanoparticles with alginate layers showed strong biofilm elimination properties. So the nanoparticles interaction with drug-resistant biofilm was also in situ studied using quartz crystal microalloys in CEM observation. And as it can be seen, the layer-by-layer mesoporous silica nanoparticles were able to penetrate the biofilm structure, degrade the extracellular polymeric matrix, and kill the bacteria due to the antibiotic release upon the virulent factor production from the pathogen. So it was also important to study the toxicity of these nanoparticles. The nanoparticles didn't affect the fibroblast cell viability and demonstrated 100% biocompatibility. The microscopic observation after fibroblast human cells exposure to the layer-by-layer nanoparticles showed that the nanoparticles didn't affect the cell morphology. So we can summarize that the imipenem was entrapped into a mesoporous silica nanoparticles framework and coated with stimuli responsive gatekeeper elastin in turn to develop smart drug delivery nanosystem. Alginate layers was decorated on the nanoparticle surface to break down the biofilm matrix and enhance the bacterial susceptibility to the nanoparticles into biofilm structures. These layer-by-layer nanoparticles resulted in better biofilm inhibition effect compared to the controls in the bulk solution of the antibiotic. The layer-by-layer mesoporous silica nanoparticles were able to penetrate the biofilm structure and kill the bacteria in already established biofilms. So the developed layer-by-layer mesoporous silica nanoparticles demonstrated biocompatibility and could be promising alternative for nanobactericides for controlling bacterial infections and drug resistance occurrence. So this work was carried out under European project Protect and the Spanish project Go to Safe. Thank you very much.
Well, yeah, I guess we have another 2 minutes break. Yeah, let's wait for 1 minute so we can start the next talk. Our next speaker is Nanka Kwanseka. Sorry to mispronounce your name. From Czech Republic. So is the speaker here? I don't think so. Chi, can you play the PowerPoint slides?
Yes.
Good afternoon, ladies and gentlemen. My name is Lenka Končická. I come from the Technical University of Ostrava from Czech Republic in Europe. And I am going to present my presentation with the title Aluminum Copper Laminated Wire Conductors, Effect of Stacking Sequence on Mechanical Properties and Structural Features. Here we can see some of the basic facts. So composites generally belong to some progressive technological materials together with other modern materials such as pseudoalloys or hybrid and hierarchical materials. And laminated composites, the type of the composites that I am going to talk about, are one of the types of the modern composites. And we are going to also look at the components of the composite and the fabrication method, because we choose the components and the fabrication method according to the intended usage of the final composites. I have chosen aluminum and copper. They are both very advantageous because they have, some of them, like aluminum, have low density, they have good conductivity and lower cost than copper. And they are also hardenable via solid solution strengthening or precipitation hardening, so they can be very well work hardened. However, they are prone to form intermetallic phases and the interfaces. So, by this reason, high temperature processing is unfavorable because of the danger of the form of intermetallics, but we can choose some different processing at room temperature, which can advantageously be done via intensive plastic deformation. Here we have chosen the rotary swaging method. The aim of this study is to prepare clad composites via the rotary swaging methods. We have chosen two different stacking sequences, we will see on the next slide. And the focus of our study was to characterize the effects of rotary swaging on the development of structure and mechanical properties within wires, which we swaged down to 5 millimeters. As we can see here, we perform detailed structure analysis and also some micro-hardness and tensile testing. Here on figure 8 now we can see how the composite looked like before swaging. The original materials were copper and aluminum with commercial purity. We assembled the stacking sequences. First one consisted of aluminum sheet and reinforcing copper wires, and the second stacking sequence consisted of copper sheet and 19 aluminum wires. Here in equation 1 we see how we calculated the reduction ratio, which was from the original 30 diameters to the final 5 millimeter diameter, and it was 3.6, which is quite a good deformation. And we performed all the analysis on transversal samples. Here we come to the results. So firstly we performed the results of mechanical properties. We can see here the original values of copper and aluminum, and in table 1 we see the values of micro-hardness which were detected or recorded after the swaging. For both stacking sequences we can see that both the components, the aluminum and also copper, increased their micro-hardness. For copper it was the highest in stacking sequence 2 for the IL sheet, and for aluminum it was in the first stacking sequence in the wires. As you can see, it was almost doubled or more than doubled. The results of tensile testing are seen in picture or figure 2. in which we have two tensile stress strain curves for both these stacking sequences. We see that the ultimate tensile strength was comparable for both the swaged composites. However, there were differences in their plasticity. For stacking sequence 1, the plasticity was very low, the elongation to failure was less than 1% of true strain. However, for the stacking sequence 2, it was more than 3%, approximately 3.5%. We can explain this phenomenon by the hardening, which occurs primarily in aluminum, and because stacking sequence 1 consisted of aluminum sheet, this means the volume fraction of aluminum was higher in this stacking sequence, so the tensor behavior was mainly influenced by this hardening of this aluminum sheet. By this reason, the plasticity was so low for this composite or for this stacking sequence. Here in these figures we can see the structures. So the original aluminum and copper structures both featured coarse grain recrystallized grains. We can see the example of the original structure of copper in figure 3a. There are also some recrystallization twins, so both the original materials were in the recrystallized form. After swaging, we acquired more or less equiaxed grains, especially in the aluminum components of both the composites. The example of such structure is seen in figure 3b, where is depicted the aluminum sheath of stacking sequence 1. In the copper components, there was bimodal structure, the example of which is seen in figure 3c. All these orientation image maps, which also depict the orientations of the grains according to the colors, depict that there were no preferential colors that would be prevailing in the structures, which means that there was no prevailing preferential texture of some very high intensity. In these figures we also see high angle and low angle grain boundaries, and the high angle grain boundaries were prevailing in both the structures, and as we can see here, we had more than 50% of high angle grain boundaries in all the components that we looked at, both copper and aluminum in both the stacking sequences. In this slide we have the results of structure analysis depicting the presence of residual stress, which means we have here internal grains misorientations in the scale from 0 to 15 degrees. 0 is depicted in blue color, and then we have the rainbow scale to 15, which is red color. In these four figures we see the aluminum sheet and copper wires, and copper sheet and aluminum wires of all the or both the composites that we swaged, and we see here that the residual stress was locally present primarily in the copper components for both the stacking sequences, and this was especially in the grains that were growing. So we saw and we see also here the bimodal structure of the copper components, and the misorientations were primarily present in the growing grains, so in the larger grains. For both the aluminum components, so the stacking sequence 1 aluminum sheet and aluminum wire of stacking sequence 2, we see that both the structures consisted of fine, more or less equiaxed grains, and the presence of residual stress or internal grains misorientation was not so significant for these components. As a conclusion, I would like to say that this study proved that the rotary swaging technology is well applicable for production of long electroconductive aluminum-copper clad composite wires. As we saw, both the swaged composite wires exhibited sufficient bonding of the component metals. We also saw that stacking sequence had negligible effects on substructure development and residual stress, We saw that both the stacking sequences featured fine-grained aluminum components with minor presence of residual stress, and we saw some residual stress in the wires of both the copper components in both the stacking sequences, and that phenomenon was mostly caused by substructure development, so by the presence of bimodal structures, and this was primarily due to incomplete relaxation during the final swaging pass. The maximum
Okay, so our next speaker is Shyamshir Sain from India. Is the speaker here? Shyamshir Sain from India. Is the speaker here? I guess not. Yeah, let's play the video.
Good afternoon. I am Shamsher Madhus Singh, going to speak on buckling and post-buckling response of composite plates under combined in plane loads. Here we're talking about functioning graded composite materials which is being utilized for civil infrastructures, especially in those applications where compatibility of material is not there. We are going to provide the functioning graded composite materials. Fiber reinforced polymer system is being intensely applied for civil infrastructure, say for example the bridges, where we find that this material has very high resistance to corrosions, and hence that could enhance the life cycle of material strength. The study have also proved that functioning graded material can be effectively used in multi-layered pavement design. So this study basically consists of mechanical characterizations, where we're talking about prediction of and evaluation of in-plane shear strength, tensile strength, compressive strength, and fragile strength of materials. Material consists of Cfrp and Jfrp independently, and then function graded composite material in form of hybrid composite as well as linearly functionally graded composites. There are some typical examples of here Cfrp and Jfrp lamination schemes here. This is that we are talking about this lamination schemes, talking about hybrid composite materials, wherein we are laying up the sequence of carbon and glass. Say for example, this CCGS represents the top two layers of carbon, then cores is the glass, and then in bottom layer is carbon. In the same way here, we are alternatively laminating or sequencing the carbon and glass layers. In that way, we can have a different hybrid composite laminates have been obtained. CCGGS, CG where carbon glass. This is bottom one say that glass carbon composite. So I had a different composites we are making, hybrid composites we are making. In the same way, we are making a functionally graded composite materials here. We said this is showing a linear gradation of carbon and glass here. This is top one is blue one. This represent the glass. Then the first layer, top layer glass is 100%. Then second layer consists of carbon and glass 50%. Again third layer 50%, and finally here whole layer is carbon layer. And then they are symmetrically disposed to the middle surface. We are making a 0, 50, 50, 100 layers. The functionally graded composite material. In the same way, we can have a different linear gradations for functionally graded composite. Curing have been done. A particular schematic have been applied for making curing the laminates. The three temperature range have been selected: 160, 120, 80 degrees centigrade, and then curing period have been selected 3 hours, 2 hours, 1 hour to find out optimum curing duration for a particular temperature. Experimental investigation, as discussed earlier, we are going to evaluate the flexural interlaminar shear strength, tensile strength, compressive strength, and compressive stress and behavior of the laminates. So this experimental investigations were done on the dynamic utility test machine with a 10-10 cavity and 3.5 where 3.5 MPa grip pressure was maintained, and for tensile test loading rate was 2 mm per minute, for compression test loading rate was 1.5 mm per minute. Sample size were taken as per STM standards. Then for flexural test we have taken the load rate was taken about 0.11 as per the equation given by this equation. That depends on span of the samples and the depth of sample and staining rating considered. This is a particular fabrication of RP laminating schemes have been shown here, where we are showing that here for proper finish where aluminum foil have been put on composite, then whole composite, weight composite have been tightened with the bolt tightening machine under the steel plate. That steel plate assembly, a hole I put in oven for a particular temperature and then cured for 1 hour, 2 hour, 3 hour duration. And after curing here, this sample have been taken out. And this sample have been taken out. After taking samples out, we have cut this samples specimens for 0 degree 5 directions, 90 degree 5 directions, and 45 degree to 5 direction for testing under ETM testing machine for different property, tensile, compression, flagellal, and interlaminar shear. Differential calorimeter used for finding the glass tension temperature of the epoxy resin. SCM, then SCM image showing here is the SCM is any electron machines was used to find out the interface characteristics of this hybrid and functional composite materials. There are some test setup for finding tensile, compression, then flagellal test as well as interlaminar shear strain, which all tests were done per FCM standards. As per shown here is summary comparison of the stresses and characteristics. We find that hybrid composites have very good response. We are having the reasonable strength with a significant deformation cavity, where carbon fiber has high strength but very low deformation cavity, and functional grade composite material has similar characteristics as glass fiber composite but slightly better strength and deformation cavity. Then for post-buckling strength evaluation, we have taken different size of cutout, different shapes of cutout. However, in this particular presentation, we are presenting the post-buckling strength under combined in plane shear and uniaxial compressions. And here we are taking the diamond shape cutout with the large size. There are three shapes of size of diamond shape cutouts have considered: small, large, and medium size cutouts. And this represents functional gradations of composite material, laminate composite material for -45, +45, 0, 90 degree orientation having taken 5 attacks each layer for each functional grade laminate. You see typical functional grade composite laminate for each layer of functional grade materials, and is this +45 or -45 represents the direction of fiber layer in each composite, and black one represents the proportion of carbon fiber, and white one represents the proportion of glass fibers in each functional grade composite material. So we have done the post-buckling strength under uniaxial compression load and plane positive and negative shear loads here. Quasi-isotopic laminate have been considered, simply separated boundary condition have been considered, and plate without cutout and with diamond shape cutout. Verification of results have been available for literature. Only the ultimate loads are different from that study. You see that one. Ultimate loads are different because of the different philosophy taken, different mechanism have been taken. In case of Baker's, ultimate load is based on loss of instability, where in the literature available literature is consist of the self-developed program based on cycle criteria and self-developed degradation models, material degradation model. This is for in plane shear under negative DS load conditions. Here this is so that the effect of under uniaxial compression shear combined loading conditions, load versus deflection response under positive load shear and load versus deflection response under negative shear load have been shown. In case of negative shear load combination, you see that response of the plate with cutouts almost very close to the plates without cutout, especially for small size cutout. For in case of cutouts with the cutout size, the D1, D2, D3, small, big, and medium and big, we will find a response for cutout. Strength of plate with the cutouts is lower than what is strength of plate without cutouts. Similar response have been done. There's an effect of load ratio have been applied for a plate without cutout, where NX by NXY represent the load ratio, that is ratio of the uniaxial compression to the plane shear load. And they find this is for positive shear, this is for negative shear. We're finding a response for the plate without cutout here, where that under in plane shear loads responses or deflections are very high for a given load. A similar study have been done for plate with cutout here. This is diamond shape cutout. Load ratio is, with increasing load ratio, we find load carrying capacity of structure decreasing. This is corresponding typical load interaction diagram I have done for combined loading conditions here. For here, this is for plate without cutout. This is for plate with the cutout. And you show that buckling and these are red lines are for ultimate failure, that is first line failure load interaction diagrams. So based on that, we are finding that some typical concluding remarks that you can make it that have the functioning grade composite materials has a better response similar to the glass fiber composite system under uniaxial compression. Combined uniaxial compression in plane shear load can give a decrease under combined loading situations. Ultimate failures are higher in functioning grade plate with fiber aligned in quasi-ectopic fiber direction under combined compression load with negative in plane shear. Increased ratio of compression load in plane shear load results in decrease in the critical buckling and post-buckling strength, especially the first ply failure load situations. And that we can also finally here can also the critical buckling, first ply failure and ultimate failure loads are higher in functioning grade hybrid composite plate subject in plane shear load with respect to uniaxial compression loaded plate. Our critical buckling, first ply failure, ultimate failure loads of the similar plates decrease when they are subject combined in plane load, that in plane uniaxial compression and in plane shear by linear load. So third strength, there are some references. I am thankful to BIS Planning for and CSIR for financial strength provided for effective execution of research work, and my student Sudhir Bumadiseti, who executed all the experimental program as well as the numerical study. Thank you very much.
Yeah, that's it. Okay. So our next speaker is Emery Khan from India. Is the speaker here? Yeah, I don't think so. Yeah, you can play the video now. Yeah, I guess it's because of the time zone issue.
Hello everyone. This work has been put forward in Triple AFM UCLA 2021 conference as an oral presentation on synthesis of polyvinyl alcohol chitosan nanofibers embedded with silver nanoparticles and its activity on breast cancer cells. Myself, Emery Khan, from the Center for Research in Nanotechnology and Sciences, Indian Institute of Technology, Bombay, India. Going ahead with the presentation, first part includes the formation of silver nanoparticles, which was done through polyvinyl pyrrolidine and glucose, in which the silver nitrate solutions was dropwise added, and further the separation of silver nanoparticles after its formation was done through centrifugation process. And later on in the second part, the polyvinyl alcohol and chitosan was used as a fiber solution in which the silver nanoparticles formed in part 1 was incorporated, and further electrospin with optimization of voltage and the speed. And in the fibers obtained, we're having particles in it, and this is the representative image. This is the scanning electron microscopic image of the fibers, confirming the morphology and formation of the fiber. The reason we opted for silver nanoparticle here is because it is present in many of the FDA approved nanomedicine, and whereas PV and chitosan turned out to be a good delivery system in which the fibers provide a high aspect ratio for controlled release of many of the medicinal product. Plus they are biocompatible and biodegradable. For the characterization, we opted first for the scanning electron microscopy to confirm the silver nanoparticle and PVA chitosan fibrous formation, wherein the spherical structure of the AGNP confirmed its morphology, and further the size also was roughly estimated to be around 60 nanometer, wherein in case of the fibers incorporated the nanoparticles showed the morphology and width to be of 200 to 300 nanometers. The inside shows that the nanoparticles are present. So further, in order to confirm about the size, morphology and the structure of the nanoparticles, we carried out TEM analysis. Transmittance electron microscopic analysis was carried out, and which shows the metallic fringes confirming that the silver formed is of metallic nature, as well as the diffraction images confirm that it is of monocrystalline nature. Then further, the spectra also confirmed that these particles are of silver, and the XRD stated the sharp peak to be of the crystalline nature. So also the dynamic light scattering index showed that the size to be nearly around 66 nanometer, and the dispersity index to be lower as 0.39. Then in order to see whether the nanoparticles were present inside the fibers, we carried out the TEM analysis of the fibers along with the, embedded with the nanoparticles. And here are the diffraction images showing that the nanoparticles which is present inside the fiber is of monodispersed nature. Further, while the area spectrum was done through the help of the EDS, so EDS analysis showed that the nanoparticles are distributed uniformly inside the fibers. Now, the absorbance of silver nanoparticles showed that the lambda max was around 420 nanometer. FTIR was carried out on the fibrous sheet, which we obtained, wherein the control was kept at PVA and cytosine, that is the plane without Ag nanoparticles, and rest of the 4 peaks showing that the spectra are showing those with the AgNP. Herein the saturation was obtained when the thickness of the fibers actually increased, and also the amide bonds were flattened a bit when AgNP was incorporated, showing that Ag and N bond were formed. Then the further, in order to study the release pattern of AgNPs, we did the analysis in DPPS, the phosphate buffer, as in the 5.6 and 7.4, showing that 5.6, that is the acidic pH, more release of AgNPs were observed. The estimation of AgNs was done to ICP-AES throughout the study. Just to confirm the mechanical property, the mechanical strength of the fibers which we obtained, we have seen that the elasticity modulus, tensile strength, as well as percentage elongation was found to be quite good with respect to the cross-linked fiber, and also when on addition of silver nanoparticles, we have seen that there is a good mechanical strength. Further, the in vitro studies was carried out to assess the biocompatibility and cytotoxicity of the nanoparticles along with the PV and chitosan fiber. So L929 as fiberelastic cell line was taken to assess the biocompatibility, and with an extract of 100 mg per ml, it was seen that still 85, more than 85% viability of L929 is present. Then IC50 value was calculated with the MCF7 MDA-MB breast cancer cell line, showing that approximately 6.93 and 7.48 of the silver ions were found to be more effective as an anti-cancerous agent. Again, this estimation was done with the help of ICP-AES, and the treatment time or the result reported is after 24 hours. Below is the morphology of the cells and the intactness after treatment at different concentrations of the PVA, chitosan, AgNPs. And the cellular uptake studies have shown that AgNPs was well taken by the cells, and rhodamine was used, was conjugated with AgNP as, and rhodamine turned out to be a fluorophore, showing the intensity as a representative image for cellular uptake of Ags. These images were taken after 24 hours of incubation and shows on the fibroblast as well as breast cancer cell lines. The antibacterial activity was further confirmed by taking the OD readings and the optical density readings after 24 hours of fiber addition. And in order to detach the bacterial cells from the fiber, we even sonicated it for 10 minutes. And further analysis shows that after addition of AGNP in both E. coli and S. aureus bacterial strain, there was a decrease in the OD when taken at 600 and 1. So conclusively, the high aspect ratio of the nanofibers assisted in the control of AGNP release and showed a very good activity on the breast cancer cell lines, wherein the biocompatibility on L929 at same concentration and even at higher concentration was reported to be well established. Nevertheless, I would like to thank Professor Rohit Srivastava, my guide and mentor and support of all time. Nanobio's lab, Bioscience and Bioengineering, IIT Bombay, India. Dr. Mayuri Gandhi, Center for Research in Nanotechnology and Sciences, IIT Bombay, India. Professor Jayesh Bellari, Chemical Engineering, IIT Bombay, India, for providing the facility with electrospinning. Ms. Preeti, Ms. Deepak from Chemical Engineering, Professor Anil, Head CRNTS, IIT Bombay, Ms. Vinita, Ms. Reshma, Dr. Gajendra, Dr. Aradhana, Ms. Priyanka, Mr. Amit, Mr. Ashish, Ms. Princey, and all of the CRNTS staff for helping me to achieve this work and the results. Also, a Department of Biotechnology, Government of India has been for funding me and providing me the opportunity to carry out this work. Thank you very much.
Okay, our next speaker is Khalid Alzabad from Southern Quabos University. Is the speaker here? Yeah, let's play the video.
Hi everybody, my name is Khalid Al-Zebdi. I am from Sultan Qaboos University, Oman. So the title of my talk for today is Date Palm Agro Waste as a Particulate Filler for Virgin and Recycled Post-Consumer Globulin. So first, I will introduce the topic and talk about our developed composites from the date palm residues and recycled and virgin globulin. Then we'll describe the methodology, which include the fiber treatment, and the biocomposite production, and then characterization, followed by results, discussions, and then I will conclude. Wood plastic composite manufacturing consumes really a high amount of wood. This will result in a serious threat to the forestry all over the world. So using agricultural residues instead actually is a good opportunity to fill in this wood shortage. In this project, we'll use the date palm agro residues to make biocomposites. Actually, date palm are available. Date palm trees are available in Middle East and in the Gulf region in high amount. So as we can see here in this graph, so the date palm is, as mentioned, in this region, the waste produced from date palm are in big amounts compared to other type of fibers from different trees. And different parts of the palm tree, actually the waste of those parts can be used as fibers, including like rachis, the midrib here, and the pedicel. In this project, we use the waste from this part, the pedicel. So the first, for the fiber treatment, so we take the waste of that date palm pedicel, and then we trim it to smaller pieces, and then we put it in water for a certain time to be able to extract the fibers in untreated form. And then we use a developed method using accelerated heating, using microwave to treat the fiber. and then we grind it in a powder form to be mixed with the BB pellets. So here we use the pulverizer to mix the BB and the powder form of fiber. DBB stands for date palm powder. So for two forms of BB, virgin and recycled. So we use a twin screw extruder to mix the two ingredients in a melt state, and then we compress it in a compression machine to make panels to be tested. So here we use 4 types of biocomposites, like BB, virgin, and recycled BB, untreated fiber in a powder form, and treated. So we develop those 4 types of composites to see the difference, the effect of the first the recycled BB compared to the virgin BB, and also the effect of the treatment on the properties, including physical properties, water absorption here we'll discuss, and mechanical properties to tensile and structural properties. And then we'll present some results for thermal degradation for all of those specimens, followed by FCM images. So for the water absorption, as we can see here, this graph, so plotted as the filler content as a function of the water absorption. So we can see for the recycled BB based biocomposite has less water absorption. When we do treatment, the water absorption will be cut more. So it will increase, of course, when we increase the fiber content, because the filler will absorb more water. For the tensile properties, for the tensile strength, here we can see the recycled BB based biocomposite has less tensile strength. That makes sense, I mean. But when we make the treatment, both will increase, and they are comparable here. And they will increase as we increase the fiber, the filler content, due to certain issues, including the distribution of the filler in the matrix, and also the interface, the compatibility between the fiber and the surrounding matrix. So for the Young's modulus, so we can see here that there is an increasing trend for the Young's modulus as we increase the filler content. And also here we can see that for recycled and virgin BB based biocomposites, they are comparable, the results. When we looked at the elongation at the break, so we can see that as we increase the filler content, the material becomes more brittle. So for the structural properties, the improvement due to the treatment was more pronounced, but similar trend also compared to the tensile strength was observed here. Okay, but more improvement, as I mentioned. So for the thermal analysis, so we can see here for the virgin BB based biocomposite, this is for untreated, and this is for treated. When we do the treatment, so the peak was shifted to the right, which means that it will bear at slight higher temperature, which means more stable. And this peak presents the evaporation of water and burning of other impurities. So for the recycled, actually we see here reverse trend. So there was no improvement in the thermal stability because the shift was to the left. So to support this by SM images for the tensile strength, for the untreated cases, we can see here there is some weak interfaces between the DBB, the date palm powder, and the matrix. This picture just a magnification of this one. So for both virgin BB and recycled BB. So we can see here some issues for the interface. After the treatment, we can observe that there is some interlocking between the matrix and the fiber. That's which contributed to the increase in the tensile strength. Actually, for both cases, for the BB treated and for the recycled BB treated. So as was presented in the tensile strength. So to conclude that we developed two types of composites from date palm agro residues using virgin and recycled BB. So the recycled BB biocomposite showed less water absorption compared to the virgin BB bio-based composites. Fiber treatment was able to cut water absorption by 65% compared to the untreated ones. Although the recycled BB bio-based composite showed lower tensile strength compared to the virgin BB bio-based composite, fiber treatment has reversed this trend, as we saw. Fiber treatment was more effective in improving the flexural strength of virgin BB bio-based composite compared to the recycled BB bio-based composites. And thermal stability was improved slightly in the case of the virgin BB bio-based composite, but was also reduced in the case of the recycled BB bio-based composites. That's my presentation, and thank you for your listening.
Okay, so our next speaker is Valentin Mangrev from France. Is the speaker here? Apparently not. Chi, can you play the video?
Good morning, good afternoon. I'm glad to present you part of my work I'm doing between two labs in France, the Cfrpifrp and the LCPO, under the supervision of Véronique Schmidt and Valérie Roguez. As a quick introduction about emulsions, you can find them in many applications, such as cosmetics, paints, food, or biomedics, and they consist in a mix of two immiscible liquids, oil and water mainly. As metastable systems, surfactants are used to stabilize the interfaces in most cases, but in the last years and decades, an alternative, as known as recurring emission stabilizer particles, are more and more studied. They present many advantages, such as a lower toxicity, a greater stability of time, and also a possibility to better control the size of the droplets. So, also, there are another topic of interest, which is the stimuli responsive nanoparticles. So here you can stabilize an oil water fluid emission, and when applying a stimulus, which can be a pH or magnetic field of temperature, you induce the absorption of these nanoparticles from the interface. And as the droplets are no longer stabilized, they merge together, we say they coalesce, and it ends up with the full macroscopic detection of your emulsion. If you encapsulate compounds inside the droplets, you can achieve an on-demand stimuli responsive release, which is of high interest for many applications. Despite this subject is more and more studied, there are some issues and challenges to overcome, such as the end life of these nanoparticles, which are released in the outer phase. Do they accumulate or interact with the target? So here lies the objective and motivation of our project is to design nanoparticles with stimuli responsiveness from biofriendly materials, but also which could be degraded thanks to the stimulus, so that no more nanoparticle would stay in the outer phase. So full degradation of the nanoparticles and destabilization of the emission. To do so, we set up this whole strategy, starting from this one, the hydrophilic polysaccharide, which we modified to bring stimuli responsiveness and bring also hydrophobicity. Thanks to this hydrophobicity, we were able to produce nanoparticles within the nanoprecipitation process. And using these nanoparticles, we were also able to stabilize recurring emissions, oil and water, and finally to destabilize them on demand thanks to the stimuli we chose, so light, pH, and enzyme. So more specifically about the modification step, in the first case, lower left, we grafted a photosensitive hydrophobic polymer, polynitrophenylacrylate, In the second case, we grafted acetals, which bring the pH sensitivity. And finally, in the third case, we grafted alkyne chains in such in a lower amount, which keeps the enzyme sensitivity properties of dextran available. So dextranase is known as the enzyme which can cut the links between the glucosidic units, and by grafting a low amount of alkyne chain, you can keep this interesting property. So with this free modified dextran, we produced nanoparticles thanks to the nanoprecipitation step. In these three cases, you can see that we obtained well-defined spherical nanoparticles with sizes ranging from 122 to 220 nanometer and a quite low PDI. So then I will describe more specifically the results we obtained with the photosensitive nanoparticles and specifically with the stabilization of Pickering emission. In these pictures and on the graph, you can see that the higher the amount of nanoparticles, the lower is the size of the droplets we stabilized. This is known as the limited coalescence phenomenon, which is quite studied, and this obtained in a reproducible way narrow size droplets. But also, we observed that these emissions are quite stable, as they are stable for more than 6 months. Then, as we grafted this photosensitive hydrophobic polymer, so polynitrophenol acrylate, this photosensitivity can be described as the photolysis of the nitrobenzyl group, which produces an acrylic acid unit, but also nitrosobenzaldehyde. This change leads to a dramatic increase in the hydrophilicity of the whole chain, and at a higher scale, we can say that light induces the photolysis of the nanoparticles. So we verify this by studying various parameters, intensity, time, to verify that our nanoparticles can be degraded thanks to UV light. And then we perform some destabilization steps in the Pickering emission system. So we cover one part of the emission and we irradiate the other part. And what we see, what we were able to see after 30 minutes is that the covered area was not experience coalescence events, while the uncovered area showed a higher size in the droplets, which show that coalescence events occurred. We also performed quite the same experiment, but this time with visible light, which is quite an improvement because nitrobenzyl group are only sensitive to UV. And thanks to this confocal microscope experiments, we were able to localize the irradiation in a specific area, and 21 droplets, which are colored in blue here, coalesced into 2 droplets in 100 minutes. So this is quite a good proof of concept that we can use our system as a reactor in a drop process. And specifically, we can the locus of irradiation can be even more specific, as we can maybe go down to micrometers. Now, moving on the results we obtained with pH-sensitive system. So with these nanoparticles, we stabilize also Pickering emission, and we showed that we also have the limited coalescence phenomenon. And we did some destabilization attempts using acidic pH. So the acetal moieties which are on the dextran chains can be hydrolyzed, and this in the with the photosensitive system leads to the hydrolysis of the nanoparticles. Nanoparticles are degraded so that the droplets of oil can merge together, and we can observe a microscopic diminution of the emission within 24 hours, whereas with the oversample at neutral pH, no destabilization occurred after 5 days. So this system is quite interesting for because it is biocompatible, as the hydrolysis of the nanoparticle produces acetone, ethanol, and dextran, and within 24 hours we are able to fully destabilize the emission. Finally, with the enzyme-sensitive system, so still we can stabilize the Pickering emission and observe the limited coalescence. We were also able to partially destabilize within 60 days an emulsion, but this can be maybe improved by playing around with the pH and the amount of enzyme we put. And these emulsions are really highly stable, as they can be stable for more than a year at 37 degrees. With the system, we were also curious if we were able to encapsulate two different compounds. So one inside the droplets we stabilize, and another inside the stabilizing nanoparticles. So to do so, we at the nanoprecipitation step, we put the Modification and the probe together, and this leads to the function of nanoparticles with inside the body key probe. As you can see on the right, these are the stack of paper emission droplets with the encapsulation of the red probe inside the nanoparticles, so at the interface, and the blue probe inside the oil droplets. The next step, which is currently working, is the encapsulation of Kinema. Finally, we were able to synthesize stimuli responsive graphite extron polymers, which are sensitive to light, pH, and enzyme, to produce narrow-sized nanoparticles through the nanoprecipitation process, to stabilize all innovator pickering emulsion with a long time stability, but also to be able to destabilize them on demand thanks to light, UV and visible light, pH, or enzyme stimuli with different kinetics, but still with good promising results. Thank you for your attention.
Okay, so our next speaker is Hannah Dupont from France. Is the speaker here? No, Chi, could you play the video?
Hello everyone, so today I'm going to present you some of the work from my PhD thesis, which deals with the valorization of cellulose nanocrystals and their use as pickering emulsion emulsifiers to synthesize different types of materials. So my PhD is run in collaboration with two labs from Bordeaux in France, so the Cfrpifrp with Véronique Schmidt and the LCPO with Valérie Roguez. So first of all, what are emulsions? So emulsions are, by definition, a mix of at least two immiscible liquids, and they have a broad range of application, as you can see here. So usually when we talk about emulsion, we think about emulsion stabilized by molecular scale surfactants. But in the case of pickering emulsion, we are dealing with emulsion stabilized by solid particles because they have better stability. We chose to work with them, but also lower environmental impact, and you can valorize the properties of the stabilizing particles. So these particles are very important to choose because their nature will impact the nature of the emulsion. So if the particle is hydrophilic, which means it's wetted by the aqueous phase, it will lead to a direct emulsion, which is an oil droplet stabilized into an aqueous medium. And on the contrary, if the particle is hydrophobic, wetted by the organic phase, then you will have an inverted emulsion, which is a water droplet stabilized into an organic medium. So in our case, we are working with cellulose nanocrystals, which are not spherical particles, but anisotropic particles with a rod shape. They can be extracted from wood, which makes them a renewable resource. But they are mainly hydrophilic by nature because they bear a lot of hydroxyl function on the surface. So to increase the hydrophobicity of these CNC, to allow the stabilization of both direct and inverted emulsion, we chose to use the esterification reaction to substitute the hydroxyl function by brominated function. So we can follow the substitution rate of these hydroxyl by brominated function over time. And as the time increases, the substitution rate increases too, with the hydrophobicity, which enables us to stabilize both direct or inverted emulsion. So the first type of material we succeeded in synthesizing were solid foams. So regarding the process, we dispersed the CNC, the hydrophobic CNC, into an organic medium here, which contains the monomers, styrene and divinyl benzene, and we disperse water inside by mixing. So we can obtain here the inverted emulsion, the water droplet inside the organic medium. And to obtain solid foam, we have to increase the water content above 64% to obtain a high internal phase emulsion, which is called HYPE. Then we are able to polymerize the continuous phase containing the monomers, so solidify it. And by washing and drying, we can isolate a self-standing modulus, a porous solid, getting rid of the water and all the residual monomers. So here you can see by FCM that the polymerized HYPE, is the exact image of the initial emulsion. So therefore, we can obtain emulsion templated porous materials. We checked the mechanical properties of this material because the presence of the CNP might have an impact on the mechanical properties because they have a Young modulus of 150 gigapascal. So by changing the diameter of the water droplet, we were able to measure different compressive modulus, but we thought that there was no impact on the diameter of the droplet on this modulus. And this was predicted by the Gibson and Ashby model. So if we see this equation, we tried to change the water fraction, so increasing the water fraction to 85% and decreasing it to 75%. And what we can see is that it fits the model except for low densities. So in the end, we obtained the porous solids with an open porosity, which means that all our pores were connected, with a tunable morphology in terms of cell size, but also of density, which fits quite well a model description. The second subject we were interested in was the polymerization of the dispersed phase this time. So similarly to previously, we dispersed the hydrophobic CNC into an organic medium, which was this time neutral, so isopropyl myristate and all from cosmetic industry. And we dispersed a polymerization system inside. So we obtained the inverted emulsion stabilized by the CNC, and we were able to polymerize these beads. So we studied two types of radical polymerization. So surface initiated ATRP, taking advantage of the brominated function on the surface of the droplet, of the surface of the CNC, and therefore from the surface of the droplet. We were able to grow this polymer from the surface of our object. And on the other hand, the free radical polymerization, making no link between the CNC and the polymer. So for the first system, what we could see that we obtained within 2 hours, very good conversion of the monomer, about 80%. And we obtained this hollow bead morphology, which shows that we effectively have grown the polymer from the surface of our emulsion, leaving an inner void inside the capsule. So, however, this reaction must be performed under a nitrogen atmosphere, which makes it quite tricky to perform. So we preferred to work with the free radical polymerization. And in this time, we obtained after polymerization full beads, as you can see here by FCM. You can see a cut inside one of the polymerized beads. It's full with polymer. So this reaction was easier to perform, and we access a similar conversion in only 6 hours, so it was reasonable. We continued with this system to assess the mechanical properties of the object. So to study the mechanical properties of these objects, we chose to work with an uniaxial compression. So we did put the sample inside the vial, and we compressed it with a rheometer. And this piece here, you can see, was pressing onto the beads, but it has a porous disc, which enables the diffusion of only the liquid phase. So here is the graph we obtained with the stress in kilopascal in function of the strain. So we imposed different deformation from 10 to 50%. And so we did the compression first. And study the compression. You can see here a linear part, which is the elastic domain. And we studied also the relaxation. And what is important to see is that before and after compression, the beads have a similar morphology. So they are still spherical, they are not broken, and they're still bear the CNC at the surface. And what is interesting to notice in this graph is that we always come back to the 0% strain, which means that they recover the entire shape. So we have a system that is deformable up to 50%, that adopts a sponge-like behavior and has a modulus around similar to soft tissues, about a dozen to 100 kilopascal, which might be interesting for bio-related applications. So we were also able to vary the number of CNC layers around each droplet from 5 to 40. As we can see here by SEM, the more dense the coverage becomes, the more aggregated the surface is. So you can see that here the surface is more dense. And by measuring the compressive modulus, what we could see is that by increasing the number of CNC layers, we also increase the mechanical properties of these latexes. Finally, the last system we wanted to focus on were capsules with control release. So these capsules were obtained by taking double emulsions as templates. So to make double emulsion, we just work with a two-step emulsification step. So the first emulsification step is to realize the direct simple emulsion, so an oil in water emulsion. So this time we use the hydrophilic CNC, so with a low modification rate. So we disperse the isopropyl state into the polymerization system with those hydrophilic CNC, and we used this first emulsion as disperse phase for the second emulsification, taking this time hydrophobic CNC, and we obtained double emulsions, oil in water in oil. We were able to polymerize it. You can see here that we have the polymerized beads with the imprints inside of the inner droplets. And this system were showed to be efficient as encapsulation vessel for both hydrophobic and hydrophilic types, above 80%.
That's it.
More than we have something that is tunable with a good encapsulation efficiency, which is transposable to other polymerization systems. So as a conclusion, we did obtain 3 types of different materials. So
okay, yeah. I can say our next speaker is ready. So yeah, you go ahead, take over. You are muted. You are muted. Hold on a second. Okay, go ahead. You are still muted? I don't hear you. Hi, Hussein. I cannot hear you. So you are not muted right now, but I cannot hear you. So there's no sound from you. Can you check your microphone? So, I think we do have your video interface. I think we do have your video, right, here.
You want me to play the video?
Yeah. Well, I guess Hossein is still working on the video, the audio issue.
Okay.
Maybe we can video. The PowerPoint slides. PowerPoint slides. Yeah, we can play her PowerPoint slides. Like,
okay.
16.
Okay. Right.
Good afternoon. maybe good night, ladies and gentlemen, everywhere around the world. My name is Hussein Kulishki. Interface and interface material characterization in multi-phase materials in general play an important role in mechanical properties and damage mechanism. Especially in composite, interface is an area between fiber and matrix with different material properties, as shown typically in the figure. On the other hand, called surface adhesion between fiber and matrix. These properties are related to silent coupling agent, and considering this area in numerical modeling can help understanding of the mechanism which composite undergo.
Hi, Chi. Is it a pause? Yeah, I guess we should unmute Mina. Yeah, I just realized now. Yeah, we should unmute Mina. That actually this talk and the next talk are from the same group. So if the Professor Hossein is not here, so Mina can take over. Let me unmute her. I guess I can.
Hi, can you hear me?
Yes, we can hear you.
Oh, I am the PhD student, Rosini Tudishki. Unfortunately, he doesn't feel well, hospitalized, so he cannot be available here, and I'm here in. The first presentation, it's not based on my project. I'm aware of the details, but here, Mr. Masoud and Mr. Amir Nava are the co-authors of this presentation, and if you have any question, they can answer. But the second presentation is based on my project, and I'm the speaker of the video.
I see. So,
do you want me to share that point? It's.
Do you still want us to play the 16, the talk 16 from?
Okay, you want me to play the 16, but it is like a design.
Please play the video if there isn't any problem.
One important parameter in interface is the thickness of interface. Usually, nano-indentation, nano-scratch tests are used to measure this thickness. And Jung and Gao, for example, calculated that to be between 0.8 to 1.5 micrometer and 0.3 to 0.2 micrometer. Also, other people used the interface thickness of 1 micrometer. Here is performing micro tensile tests for single fiber matrix specimen. For this purpose, a small testing machine was made in our laboratory in which the tensile tests were performed by applying zag plate. The resulted displacement and strain were measured by digital image correlation technique. And using the obtained experimental displacement result from VIC and performing finite element analysis of the specimens, the average interface mechanical properties were obtained. In this method, specimen size is also very important, so we consider the specimen dimensions as small as. To make the specimens, we actually initially made silicon mold using laser cooking. And for metrics, we used actually K-epoxy resin hardener as mentioned here. The hardener resin percentage of 10 and 13 were used, fiber was D-glass, and the mixing time was 5 minutes, and curing condition was 24 hours and 45 degrees centigrade, and 6 days in. We made 3 categories of specimen. The category was standard specimen. Actually, we may call that in the other slide macro specimens according to FCM standard. Smaller, wide and thickness specimens, which we call them micro, one category without fiber, and one category with single fiber. See the wide thickness and hardener resin percentage of various specimens. Suppose that when we say that one is a specimen without fiber, and then say that 1F, we mean that the specimen with a single fiber. And as you can see here, we consider 6 categories of specimens, different hardener resin percentage, different wide, and different thicknesses. Before starting the micro specimen testing, we performed standard macro specimen tensile test based on STM-D638-14 without fiber to actually calculate the proper mechanical property of metrics. These are the hardener resin technique. And repeat the test. You can see the small machine that we made in our laboratory for micro testing. And this is the weight that we are using as a actually load, and the measurement of each specimen, thickness and micro, and for VIC equipment, we use a Canon camera with 50 frames per second and 90 to 20 times 10, 80 pixels for each. For each specimen, we performed a random pattern of spots using spraying of things by hand. Software. We consider the extensiometer lengths of 3 millimeters in the software, and we use also binomial filter for each specimen. Therefore, we find the displacement lengths.
Hi, Qi. I think we can move on to next speaker.
Okay.
Yeah. So, yeah. Mina, right? So, please unmute Mina so we can let Mina talk now for her presentation.
Thank you so much. But unfortunately, there's some problem. It seems that there's some problem with laptop, because with laptop hear voice, maybe the microphone on my laptop some problem. So I think that's better to play the video. I don't know. Is there any way?
Okay, yeah, we can play the video. The 17. Yeah, could you play the PowerPoint slides?
Hi everyone, I am Mina Jahan Mardi, a PhD student at American University of Technology under supervision of Professor Hosseini Tudeshki. It's my pleasure to have this opportunity to share my studies with you during this conference. The title of my study is the experimental and numerical behavior of polyurethane material using a modified hyperviscoelastic constitutive model. During this presentation, I will talk about some contents. First of all, I will introduce the elastomer material. Then I will explain the developed theory which is used to model the behavior of this material. After that, I will explain the procedure of the experimental and numerical analysis. The next part is the FEM modeling of uniaxial tension test. Then I will discuss about the damage evolution in elastomers, and at the end, the conclusion. The elastomer materials are widely used in different industries. For example, the non-pneumatic tires, which are the new generation of tires. Another example is the pipeline inspection gauge or PIGs, which are used in oil and gas industries. The body of these instruments made from the elastomers. Or in biomedical engineering, for example, many artificial tissues for the body are made from the elastomers, and also in aerospace engineering. So I think that the study about these kinds of materials can be useful for the industries. The elastomer materials are divided in two groups based on their shore hardness. Shore A for flexible material and shore D for rigid material. The shore hardness of elastomer is calculated based on ISO 868 standard. As we can see in the chart, these materials based on the shore hardness number divided in different groups from extra soft to extra hard. The elastomer I used in this study is polyurethane in the group of shore A with three different shore hardness number 60, 75 and 85 in three different groups from soft to medium soft and medium hard. To develop an analysis theory, at first we need to notice that the behavior of the elastomer is highly nonlinear in comparison with the other types of material, as we can see in this picture. So there is no direct relation between the stress and strain for these types of materials. So we need to use the strain density function to calculate the stress-strain relationship. These are some known strain density functions which are used mostly: the Money-Rivlin function, Ogden, Nehukian, and Marlow function. The coefficients of these strain density functions should be calculated by doing some experimental tests. And these strain density functions can simulate the hyperelastic behavior of the elastomers. As I told, to calculate the stress of this type of material, we need to use the strain density function. By following this procedure and by assuming that this type of material is incompressible, we can calculate the stress of this type of material in terms of strain density functions and the left Cauchy-Green deformation tensor. The elastomers have two different behaviors: hyperelastic behavior and viscoelastic behavior. Hyperelastic behavior is related to the highly nonlinear behavior of these materials, as we discussed in the previous slide. And the viscoelastic behavior, which is related to the hysteresis, which we can see in the stress-strain curve of these materials during loading and unloading. In the previous studies, most of the researchers used the rheology model to simulate the viscoelastic behavior of these materials. which is time consuming and has some difficulties in calculation. In present study, I have tried to simulate both the hyperelastic and viscoelastic behavior of this material by writing the user material subroutine linked to the Abacus software. In this subroutine, I use the strain density function of Munir-Rivlin with 9 coefficients to predict better and more accurate hyperelastic behavior of this material. And to simulate this viscoelastic behavior, I have used the dynamic increase factor multiplied to the strain density function to make a hyper-viscoelastic density function. As we can see, this is the Munir-Rivlin strain density function with 9 coefficients. So I had to do some experimental tests to calculate these 9 coefficients of Munir-Rivlin model, and also to calculate the A and B, the coefficients of the dynamic increase factor, which representative of the viscoelastic behavior of the elastomer. In the following, to predict the damage evolution, I have used the hyperviscoelastic elements based on the user material subroutine equations that I discussed in the previous slide, and the cohesive elements for the damaged area based on the bilinear traction separation constitutive model. As I discussed, to calculate the 9 coefficients of the Munir-Rivlin model and the coefficients of dynamic increase factor, I had to do some experimental tests. The tests I've done are the uniaxial tension test based on the ASTM-412 standard. These tests performed for all 3 shore hardnesses of the polyurethane under varying strain rates from 0.001 per second to 0.33 per second. These are the procedures I followed to calculate the coefficients. For calculate the dynamic increase factor coefficients, means A and B, at first we need to plot the stress strain curves, then calculate the area under the strain curve, which is equal to the strain energy, and then plot and feed the data of ln epsilon dot star versus ln of dynamic increase factor minus 1. Then we can calculate the A and B, the coefficients of the dynamic increase factor. In the other procedure, to calculate the Munir-Rivlin coefficients, at first we need to plot the stress strain curve, then we need to use the curve fitting to calculate 9 coefficients of the strain density function. In this slide, we can see the engineering stress versus engineering strain curves for different shore hardness of polyurethane in different strain rates. As we can see, by increasing the strain rates, the hardening behavior of material is increased too, and also by increasing the shore hardness of the material, the maximum stress of the material is increased. By using some equations, we can derive the true stress versus true strain data from the engineering stress-strain data. As we can see in this picture, these are the diagrams of true stress versus true strain for the polyurethane with different shore hardnesses and different strain rates. As I discussed before, by following the procedures, we can calculate the 9 coefficients of Munir-Rivlin model and the coefficients of dynamic increase factor. In this picture, in these tables, we can see the calculated coefficients of the Munir-Rivlin model from C01 to C03, and A and B, which are the coefficients of dynamic increase factor for different shore hardnesses of the polyurethane at the strain rate of 0.33 per second. In the next step, I've done a finite element modeling to compare the experimental and numerical result. In the right picture, we can see the dumbbell specimen under uniaxial tension loading in experiment, and the left picture shows the results of specimen under uniaxial tension loading in Abacus software linked with the developed user material subroutine. As we can see, there is good agreement between the experimental and numerical results for all three shore hardnesses. So it can be concluded that the developed hyperviscoelastic constitutive model can predict the behavior of the material with good accuracy. To predict the damage evolution in this material, a pure shear specimen was modeled in the Abacus with the material properties of the polyurethane with shore hardness of 75 and a strain rate of 0.33 per second. The elements of upper and lower sections are related to the hyperviscoelastic material model with developed user material subroutine equations, and the elements of the middle surface in the following of the key situation line are the cohesive elements with the bilinear traction separation law. Right, we can see the experimental and numerical results of the damage evolution. The left pictures show the damage evolution in Abacus model in three different time increments, and the right pictures show the damage evolution in experimental tests. You can see the good agreements between the numerical results.
Can we stop the video just for a moment? So I just want to check if our last speaker is in the session. So is our last speaker Linus Ganthier from France here? The last speaker our session, Linus Ganthier from France, are you here? And we don't have video, recorded video, right?
Oh, we don't have it.
Yeah, that's how. Yeah, let's just play. Let's continue. That's why I asked. Let's continue play Mina's video, so we can.
Okay.
Then that will conclude our session.
Okay.
During this.
Yes, about here. That's fine. Yeah.
I'm not sure whether it doesn't come with the sound this time.
I see.
Maybe I will just go to the.
During this study, a user material subroutine with a hyperviscoelastic strain density function, which is the combination.
So we don't have a sound.
Yeah, I don't know what happened this time.
Yeah, I guess we are almost on the conclusion. Yeah, I guess the virtual meeting is still not the same as face to face. There can be so many.
Function with 9 coefficients and the viscoelastic dynamic increase factor was developed to predict the rate-dependent and nonlinear behavior of elastomers. And the simulation of the material behavior in Abacus showed a good agreement with the experimental data. In the next step, the proposed hyperviscoelastic constitutive model with cohesive zone elements were used to predict the damage evolution in pure shear specimens. And also the experimental and numerical results showed a good agreement. By investigating more about the results, we can conclude that by increasing the shore hardness, the maximum stress and the slope of the stress-strain curve are increased too. And also by increasing the strain rate of loading, the maximum stress and hardening behavior of the elastomer are increased as well. Totally, it seems that we can conclude that the form methodology is able to predict the damage evolution in elastomer materials.
Okay, so thanks for everyone's participation. Especially, I want to thank for the technical experts from UCLA, especially Qi Qian. So thank you very much. So let's conclude the session and enjoy the rest of your day.
Thank you, Dr. Liang.
Yeah, thank you very much. Bye, everyone.
Bye.